Oh, didn't see you there. It's just reading up on some of my Laplace. Time really flies. When I sat down, it was 3 o'clock, and oh, geez, it's 6 over S. Huh. Where does the time go? The S domain. That's where. Well, while you're here, I'll tell you a little bit about Laplace. The Laplace transformation was invented by Pierre-Simon Laplace and is essentially a transfer function to take complex functions in the time domain into the S domain, essentially a complex exponential domain. Laplace, the general form of Laplace, is the integral from 0 to infinity of f of t, that function in the time domain, times e to the negative s of t dt. Now, there are some limitations using Laplace. Your function has to be an LCCDE, or linear constant coefficient differential equation, and the initial conditions cannot be 0. Also, keep in mind, it's extremely useful if your f of t is a complex fraction to break it down using partial fraction decomposition into smaller, simpler fractions so you can use the Laplace transform tables and don't have to keep on doing all those pesky integrals. Matt will show you an example later. Now we're going to give you an example in which you need to use Laplace to solve a linear constant coefficient differential equation. Our LCCD models human physiology of morphine drip. The x portion of our equation represents the morphine drip and its activity in the human body. The y portion represents the metabolism and elimination of the morphine after its pain-killing properties have been used. We would like to calculate the impulse response, or h of t, of this equation. As you'll notice, this equation is extremely complex in the time domain and will require quite a vast knowledge of differential equations to solve. However, using Laplace, as Matt will now show you, simplifies the solution quite a bit.
Right, so as Mike said, we do have a linear constant coefficient differential equation, and we want to find the impulse response, or h of t. Now we know h of t is related to the transfer function, or h of s, to the inverse Laplace transform, but really missing a link to kind of link this LCCDE to the transfer function. That link is going to be that the transfer function equals h of s over x of s, which we can easily get by dividing the LCCDE, which we're about to do. So the first step in solving this equation is going to be to transform from the time domain to the s domain. So the first step is to factor out the x, factor out the y, and wherever you see a prime, you're just going to put an s. Now we can ignore the initial conditions here because the transfer function assumes the initial conditions are 0. So once we have it in the s domain, all you have to do is simply divide by x, and then divide by the coefficient of y sub s. So in this case, it's a very simple division, but the answer you get is very messy. It's very hard to take the inverse Laplace of this current form. So to solve this further, we need to do a partial fraction decomposition. In order to do that, the first step is to factor this denominator. So in this case, it's going to factor 2s times 4s plus 64 times s over 3 plus 4. And then once we get the denominator factored, we can go ahead and use MATLAB or Wolfram Alpha to get this partial fraction decomposition. So in this case, we end up with 3 terms, and this is going to be much easier to take the inverse of. But just to make it a little bit more obvious, we need to get this in the form of the inverse Laplace tables, which we're about to do. So we're going to go ahead and split up this numerator into this s term and this coefficient term. So we're going to go ahead and get 87s over the denominator and a 4 over the denominator. And then these 2 other terms are just going to remain. Again, one more simplification step is necessary. So we're going to go ahead and factor out this 87, and we're going to get s over s squared plus a squared. We can do that right from the table. We're going to get a over s squared plus a squared. Again, you can consult the table. And then you're going to get a coefficient, 1 over s, another coefficient, 1 over s plus a. Both of these forms we can also take right from the table. So the final step is to convert from s domain to time domain. So this s over s squared plus a squared becomes a cosine term. The a over s squared plus a squared becomes your sine term. 1 over s just simplifies the coefficient, and then this 1 over s plus a becomes this e to the negative at term. But we have to remember that this is a causal system. We therefore need to multiply this entire answer by the step response, u of t, and then this is going to be your final answer. So this entire thing is your impulse response. Now at this point, you can go ahead and ask yourself, based off the problem and the equation, does this answer make sense? And you have to see that it depends on the sinusoid. So we can see that based on the morphine drip, it's going to be inputted, where you're going to see an increase in activity. It's going to peak, and then the body's going to start to eliminate the drug until the next drop comes for the increase. So there you have it. That's the solution.
Okay, so thanks to Matt for giving us some insight on how the Laplace transform works and giving us a great example of it. And now we're going to go into more of a real-world example to show what bioengineers are using these equations and this knowledge to better themselves and make advancements in the medical field. So we're going to refer to a paper titled "The Phase Lagging Model of Brain Response to External Stimuli, Modeling of Single Action Potential." And this paper focuses mostly on the neuron and the impulses that they give and receive to control the brain and how it works. So we know the brain is an extremely important and very complicated part of physiology. Modeling the brain and its components has become an integral part of medicine and bioengineering a lot over the past few years. The knowledge of how it works is going to make a huge impact on what we do down the road and how we focus all of our intelligence. So the paper is about focusing on the scientific principle of the stimulus of the neuron by signal and monitoring its output. They do this by monitoring the voltage, and this voltage is due to the permeable membrane, that is the sodium plus and the potassium ions that are creating a potential difference across the membrane. So with this potential difference, they're able to get the voltage, transform it into a current, and then use Laplace transforms with these very complex equations to simplify all their calculations. And as you can see, here's a picture of a few things they did with the Laplace transform. And it really helped them simplify things down by setting some conditions to 0 and crossing out a lot of the terms. So you can see, just like in the example Matt did, how useful these equations were. And how powerful they are in different aspects if you look in different research papers. So thank you for watching our video, and hope you learned.